Welcome back to my channel Easy and Inspire. In previous session we have seen what is a counter and what are the different types of counters. In today's session I am going to discuss about asynchronous counters and types of asynchronous counter, and I will discuss first type of asynchronous counter. See, what is an asynchronous counter? Asynchronous counter, see, the name itself says there is no synchronization. So as we have already discussed, consider I am taking 3 flip-flops like this. You can consider 4, 5, 2 or whatever the number you want. For the first flip-flop, see, for the first flip-flop we are applying clock pulse, but not for the remaining. For the remaining flip-flops, the previous outputs are given as clock pulses. See, please remember this point. For the first flip-flop, external clock pulse is applied, and for the remaining flip-flops, previous outputs are given as clock pulses, either Q or Q bar, whatever you want. See, like this we are going to apply clock pulses. Okay, that is the very important point in asynchronous counters. The state change does not depend on the clock pulse applied. Okay. Here, ripple counter is the another name for asynchronous counter or example for the asynchronous counter. In today's session, I am going to discuss about what is a ripple counter and one type, ripple up counter. We know up and down, two types of counters to count in two different ways, for up counting, for down counting. In today's session, I am going to discuss about ripple up counter. See here, n bit ripple counter has 2 power n states. Consider I am taking 3 bit ripple counter. It is having 2 power 3. 8 states means from 000 to 111 means 0 to 7. It is in up counting 0, 1, 2, 3 like up to 7 up counting. In down counting 1, 1, 1 to 0, 0, 0. It means 7 to 0. It is called as down counting. So, n bit ripple counter is going to produce 2 power n states. 2 bit ripple counter is going to produce 2 power 2 4 states. 4 means 0, 0, 0, 1, 1, 0, 1, 1. See, 0 to 3. It is in up condition. In down condition, 1, 1 to 0, 0. 3, 2, 1, 0. This is down counting. So, n bit ripple counter is having 2 power n states. It is also known as mod n counter. Okay. So, ripple counter, why we are calling it as ripple counter? Because the clock pulses, see, the clock pulses ripples it propagation. See, the way of clock pulses, how it is going to be, we will see in the next slides. Okay. So, two types of counters. So, ripple up counter and ripple down counter. In today's session, we are going to discuss ripple up counter. So, we know ripple counter is nothing but it is another name for asynchronous counter, where, so I will again draw here, and very important point I will explain. Please pay attention. Consider I am taking 4 flip-flops. So, consider I am taking 4 flip-flops. It means n bit. So, here n is nothing but 4. 4 bit flip-flop is having 4 flip-flops. 4 bit counter is having 4 flip-flops. 3 bit clock counter. 3 bit counter is having only 3. 5 bit counter is having 5 flip-flops. See, the number of flip-flops present in the counter depends on the number of bits n. So, n is nothing but number of bits. So, n equal to 2, then only 2 flip-flops are enough, and 2 power 2, 4 states it is going to produce. If n is equal to 3, we need to consider 3 flip-flops only, and it is going to produce 8 states like 0, 0, 0 to 1, 1, 1. So, number of flip-flops required is equal to number of bits Okay. So, and one more important point, consider again, I am taking 3 flip-flops like this, and clock is applied to the very first flip-flop, and it is going to produce some output. Okay. Now, this output, whatever the output you got here, Q bar, right? So, this is Q bar in every flip-flop, Q bar, again Q bar. So, the first flip-flop to which we are applying clock, it is going to produce LSB. See, LSB. And so, like this, we have to go, and the last flip-flop is going to produce MSB. So, this is very, very important point. So, for which we are applying external clock pulse, it is going to produce LSB bit, and last one is going to produce MSB bit. And in ripple counters, we are considering toggle states or toggle mode of operation. So, we can consider JK flip-flop or T flip-flop to design ripple counters. So, these two are very, very important points. See here, this is the block diagram of ripple counter in which I am going to consider JK flip-flop to design this ripple up counter. See, ripple up counter. So, this circuit or this block diagram is used to count. See, 1, 2, 3. 3 flip-flops means 3 bit. So, 3 bit ripple up counter is this one. So, 3 flip-flops. So, 3 bit ripple up counter. Up means from 0 to 2 power 3 means 8. Total 8 states. 0 to 7. So, 0 to 7 means 0, 0, 0 to 1, 1, 1. In this way, I am going to count my states from 0, 0, 0 to 1, 1, 1. 0th state, 1st, 2nd, 3rd up to 7th state. Okay. So, if you want to know about this operation, please, if you don't know JK flip-flop operation, just go through this link and watch this video, then you will get clarity. So, see here, clock pulse is applied to the first flip-flop. This is my first flip-flop, and clock pulse is applied here. Only for the first flip-flop, I am applying clock pulse. This output is nothing but LSB of my output, and like this I have to go, and the last one is MSB. For the second flip-flop, Q bar is considered as clock pulse. So, for the second flip-flop, Q bar is clock pulse. For the third flip-flop, Q bar is my clock pulse. So, if I am having fourth one, again Q bar is my clock pulse. You can consider Q bar. So, here in this case I am considering Q bar as my clock pulses. Okay. Once again I will explain. Please pay attention. So, here I am considering 3-bit ripple counter. 3 bit. So, I am taking 3 flip-flop. For the first flip-flop, clock pulse is applied because it is asynchronous. For the second flip-flop, Q bar is considered as clock pulse. For the third flip-flop, again Q bar is considered as clock pulse. You can take Q or Q bar. In this up counter, I am considering Q inverse. See, Q1 bar, Q2 bar as clock pulses to the next flip-flop. And we know that JK flip-flop, see here, we know that JK flip-flop is going to produce output only when input is high. J equal to 1, K equal to 1 condition. In J equal to 1, K equal to 1 condition, output is toggled. We have already seen, see here, we have already seen we need to consider toggle mode for operation. In JK flip-flop, so J and K, these two must be 1 to get toggle condition. So, see here, I am taking logic 1 to all the JK inputs. So, 1 and 1, 1, 1, again 1, 1. So, in this condition only, output is toggled from 0 to 1 or 1 to 0. So, toggling means changing its state. Okay. Now, we will see the operation. So, JK flip-flop has toggle condition only when J equal to 1 and K equal to 1. So we have applied logic 1 to all the inputs. And next point is toggle means state changing from 1 to 0 or 0 to 1. Okay. And state count. See, we have already seen counting. Counting is done by taking the outputs. So outputs of each and every flip-flop. And we have to consider the output of each and every flip-flop and write down from MSB to LSB. So output of this one here, again output of this one, again output of this one. So write down and it gives the state number. Okay. So in the above block diagram, we are considering 3 flip-flops. So 2 power 3, 8 states from 0 to 7. So 0, 1, 2, 3, 4 up to 7 states it will give. Now we will see the operation clearly. So before going to explain the operation, I will explain here. This is the truth table of this counter. So this is the truth table of ripple up counter. See here, count is 0, 1, 2, 3, 4 and count is increasing. So it is called as up counter. How? We can say it is 1, 2, 3. I will explain here. Q3, Q2, Q1. The value of Q3, Q2, Q1 is 0. 0, 0, 1 means 1. 0, 1, 0 means 2. 1, 0, 1 means 5. Like this, we need to write the count value. So this is the clock pulses applied, number of clock pulses applied. See here, Q3, Q2, Q1. Why you are going like this? Always we will write data from MSB to LSB. So MSB and middle values here LSB. So MSB to LSB we are going to write. See, MSB to LSB, or you can say LSB to MSB. So whatever the values or output values you got here, write down one by one in the truth table, and the value of the output is nothing but the count. So here we are considering 1, 2, 3. 3-bit ripple counter. See here, 3-bit ripple counter. So output is varying up to 0, 0, 0 to 1, 1, 1. The output is going to vary from 0, 0, 0 to 1, 1, 1. Total 8 states it is going to count. After 8 states, it is going to be 0, 0, 0. Means again it is resetted. The counter is resetted at this point. So the count is 8. So we will see how it is going to be appear. So now I will explain. Before that, I just want to mention few points. So we need to consider toggle condition of JK flip-flop to operate as a counter. We have already discussed. So it is going to be toggle when J equal to 1, K equal to 1 and clock is applied. See here, J equal to 1, K equal to 1 and clock pulse is applied. Then that is toggle condition. Means 0 is going to be 1, 1 is going to be 0. So this is nothing but state change or toggling. Now I'll explain the operation. See here, clock pulse I'll take like this. Clock here and Q3, Q2, Q1 values. So Q3 value, Q2 value, Q1 value and state count here I will write. So this is my table. Initially I am considering all outputs 0. See, 0, 0, 0. So I am taking Q3 0, Q2 0, Q1 0 and clock is also not applied. I am taking this as 0 clock pulse and my count is 0 because 0, 0, 0. So count is 0. This is state count. Okay. Now logic 1 is applied to all the flip-flops as input. So 1, 1. Again 1, 1, 1, 1. Okay. And clock is applied to the first flip-flop. This is first flip-flop, second, third. Clock pulse is applied to the first flip-flop. So see here, J equal to 1, K equal to 1 and clock pulse is also applied. So I am considering positive going clock pulse here. Then output is toggled. I'll take one more color. So output is toggled and it is going to be 1. See, initially 0, 0, 0. Now after applying the input and clock pulse, output is toggled to 1. Q1 is 1. So this is Q1 I'm writing it as 1. Okay, it is 1. So it is 0. Because see here, Q1 is 1, Q1 bar is 0. 0 is given as clock. So 1, 1 and clock is 0. So there is no change in this flip-flop. So whatever the previous output, it remains the same. 0. So it remains same. So there is no change in the third one also. So no change. So again it is 0. First clock pulse is applied and count is 1 here. Now we will see second clock pulse. I will take one more color. Okay. Okay. Now second clock pulse. So second positive going edge I am taking here. So 1, 1 and clock pulse is applied here. So clock pulse is applied and 1, 1. So output is going to change from 1 to 0. Output is toggled. So Q1 is 0. I am writing here 0. It is 0 means Q inverse is 1. 1 is applied to the second flip-flop. See here 1 is applied to the second flip-flop. 1, 1 inputs and clock is applied. So it starts activated. It activated and output changes from 0 to 1. See, output change. Q2 is 1. Okay, it is 1. So Q2 inverse is 0. 0 is applied to the third flip-flop as clock pulse. So 0 is applied. 1, 1 is inputs. So no change in the output. So 0 is my value. This value is 0, 1, 0 means 2. Similarly, I'll explain one more. I'll take third color. Okay. Third clock pulse. So see my third clock pulse. Third clock pulse is applied to the first flip-flop. Please remember third clock pulse is applied and 1, 1 are inputs. 0 is changed to 1. See, 0 is changed to 1 here. So it becomes, see, this one becomes 0. Because it is 1, Q inverse becomes 0. 0 is applied to the second flip-flop. So before that, what is the value here? Q1 is 1. I'll write here. Okay. 0 is applied to this one. So 0 is applied and inputs are there. So there is no change in the flip-flop. So whatever the previous value, 1 is my previous value. It remains the same. So this is not changing. So this one is also not changing. So similarly, without any, so this is not changed. So there is no changes in the third flip-flop. So directly I'll write here 0. 0, 1, 1 means count 3. Like this, you need to do the remaining. See 0, 1, 2, 3. Count is increasing. So after 7, so after 1, 1, 1, how it is going to be 0? I'll explain that one. So up to 8 counts, it is going to count. After that, it goes to reset condition. I'll explain this reset condition. See here, 0, 0, 0, 0, 0, 1, 0, 1, 0. Like this, you'll get 1, 1, 1 up to 7. So total counts are 8. So this counter is going to count up to 8 states. So what will happen after 1, 1, 1? See here, I'll explain. Okay. So 1, 1, 1. So my previous outputs. Okay. Now clock pulse is applied to this one. See, after 1, 1, 1, clock pulse is applied. So 1, 1 are my inputs to all the flip-flops and clock is applied to the first one. So it is going to change. So 1 is changed to 0. So Q1 becomes 0. Okay, it is 0. So Q inverse becomes 1. 1 is applied again as clock pulse. So it is again toggled to 0. So it is also 0. This is 0 means it becomes 1. 1 is again applied as clock pulse. So again it is toggled to 0. So 0. 0, 0, 0 means counter is resetted. So this is the reset condition. So this is about truth table of ripple up counter. This is the timing diagram. See here, initially Q2, Q1, Q0 or Q3, Q2, Q1. So what it may be? Or zeros. After first clock pulse, it becomes 0, 0, 1. After that 0, 1, 0. Next 0, 1, 1. So 0, 1, 2, 3, 4, 5, 6, 7. After 7 clock pulses, after 8 clock pulses, it becomes again 0. Total state count is 8. So this is about timing diagram of 3-bit ripple up counter, that is also called as Mod-8 ripple counter. Please pay attention, this is very, very important. 3-bit ripple up counter or Mod-8 ripple counter. Similarly, we can design 2-bit or 4-bit. 2-bit means we have to consider 2 flip-flops only. So it is going to count up to 4 states, 0, 0, 0, 1, 1, 0 and 1, 1. Similarly, 4-bit ripple counter is having 4 flip-flops and outputs are varying from 0, 0, 0, 0 to 1, 1, 1, 1, means total 16 states. So in next session, I will discuss about ripple down counter. Thank you.